All right, so what I want to do next is, previously we talked about a formula for the change of basis between any two bases. Specifically, we're talking about bases over R2, just kind of as our starting point. That's going to be the easiest place for us to start. What I want to do is I want to give you kind of an alternative version of the formula that we developed, or at least another way to think about. It's the same formula, actually, but I at least want to think about another way to go about thinking about this formula. And then I want to do an actual example. I think that an actual example here would be very helpful. And so what I want to do is I want to go through and I want to do the following. So I'm going to let B prime and B double prime be two different bases for R2. And the bases that I'm going to choose, so the first basis is going to be the basis 1, 2, comma 3, negative 1. So nothing special there. The basis B double prime is going to be the basis 2, 3, comma 4, 5. And again, these are just bases that I just made up. They have no special qualities about them at all. The only thing that you'll have to check is that they really are two basis vectors. So that's B prime and B double prime. And then what I want to do is I'm going to kind of work with, again, just some arbitrary vector. I'm just going to pick 1, 3 just to pick something concrete that we can work with over and over. And what I want to do is the following. So I want to compute or find the following. So I want to find the vector v with respect to B prime and the vector v with respect to B double prime. Okay, with respect to both basis vectors. I want to compute the basis vectors in B prime, so 1, 2, and 3, negative 1. I want to compute those with respect to the other basis, B double prime. So I want to compute 1, 2 with respect to B double prime, and 3, negative 1, again with respect to B double prime. And then finally I want to compute, so lastly I want to compute, it's hard to say this without giving away the story here, but I want to compute the vector v. Here's what I want to do. Here's a better way to explain this. I want to find the matrix M. By the way, I'm just slightly annoyed and slightly distracting myself because I wrote these in kind of a funny order here. So A, I want to find the basis vector v with respect to B prime and B double prime. Secondly, I want to find the basis vectors in B prime with respect to B double prime. And lastly, what I want to do is I want to find the matrix M, where I can take the vector v with respect to the basis B double prime and write this as M times the vector v with respect to the basis B prime. Okay, so that is what we're after. And this is going to give us, again, another alternative way to think about this change of basis formula that we talked about last time. I find this computational way to be much easier. I wanted to be sure to include this video because I find it so much easier, and it's much more intuitive, I think, too. So let's get to work. So for the first step, I've done all these calculations ahead of time just to save us a little bit of computational trouble, but you should really verify all these formulas that I'm putting in front of you here. So the first is, what I want to do is I want to find the vector v with respect to B prime and B double prime. So that means that I want to solve the vector equation 1, 3 is equal to A times 1, 2. This is not a half, but just the vector 1, 2, plus B times the vector 3, negative 1. So I want to solve that for A and B. And it turns out when we do that, what we're going to get is 1, 3 with respect to B prime is going to be our values of A and B that we get when we solve this. And it turns out that that's going to be 10, 7, and negative 1, 7. Okay, so 10 over 7 and negative 1 over 7. So that is our vector v with respect to b prime. And we need to solve, and we need to do the same thing, but with respect to the vector b double prime. So b double prime was the vector 2 over 3, not 2/3, but just the vector 2, 3, plus 4, 5. Okay, and so what that means is that our vector, I don't know why I keep writing fractions, that's annoying. The vector 1, 3 with respect to b double prime is going to be the vector CD, where C and D are solutions here, and you can solve this system. You end up with 7/2 and negative 3/2. I did not set anything up ahead of time to be nice, so we do end up with fractions. Hopefully that is not off-putting here, but yeah, but this is just a general setup. I didn't pick any of these numbers ahead of time to work out nicely so that they're integers, so we are going to end up with these fractions. So that's what we wanted to do for A. Okay, so this is our v with respect to b prime and v with respect to b double prime. So that's what we wanted there. All right, next up what we're going to do is I want to compute the basis vectors in b prime with respect to b double prime. So a very similar thing that we want to do, what we want to do is we want to take 1, 2, and write this as, we want to write this in with respect to b double prime. So this is going to be c times 2, 3 plus d times 4, 5. Okay, so that's going to be our basis vector 1, 2. And so that means that our basis vector 1, 2, I want to make sure I write this the right way. So 1, 2 is going to be CD with respect to B double prime. And it turns out if you solve the system, you end up with C is 3/2 and D is negative 1/2. Okay. Likewise, we want to take the other basis vector in B prime, which was 3, negative 1, and write this in the form as a linear combination of 2, 3 and 4, 5. And when we do that, we end up with 3, negative 1 being written as the vector CD with respect to B prime, where C happens to be negative 19/2. I told you I didn't pick these out ahead of time, so we got ugly numbers. Negative 19/2 and 11/2. All right, and so that's with respect to B double prime. Okay, so we get 3/2, negative 1/2, negative 19/2, 11/2. And then C, it turns out, well, before I ruin the story here, C, remember what we wanted is we wanted to find M so that the vector V with respect to the basis B double prime is equal to M times the vector V with respect to the basis B prime. And it turns out that M is going to be nothing more than the 2 by 2 matrix whose columns are 3/2, negative 1, 2, and negative 19/2, 11/2. So we get 3/2, negative 1/2, 19/2, negative 19/2, 11/2. It turns out that that's M, and we can check, and I would encourage you to check that this really does happen, right? If I take V with respect to B double prime, so that was 7/2, negative 3/2. So if you get 7/2, negative 3/2, that really will be equal to M. which is 3 halves, negative 1 half, negative 19 halves, 11 halves, times, times v with respect to b prime, which was 10 over 7, negative 1 over 7. So if you multiply these out, you really do end up with, you really do end up with 7 halves, negative 3 halves. Okay, so this is again another way to view the change of basis formula. So let's just recap what just happened. And so what I want to do is I want to state this for general bases b prime and b double prime. This actually works for arbitrary vector spaces, whether they're Rn or whether they're matrix vector spaces or polynomials or whatever. It doesn't really matter. This works for arbitrary vector spaces. Let's say that we have two vector spaces v that have the bases b prime. Just going to have, say, a basis v1, v2, v3, all the way out to vn, and b double prime, which is going to have, say, the basis w1, w2, all the way out to wn. Notice that these have to have the same number of vectors because they're a basis. The number of vectors in any basis has to be the same. That number of vectors in the basis is called the dimension of the vector space. Okay, so it's going to be the same regardless of whatever our basis was. And so what we want to do is we want to find the matrix M. We want to find the matrix M so that for any vector v, we have v with respect to the basis b double prime is equal to m times v with respect to the basis b prime. So I'm not going to prove this, I'm just going to state, really it turns out that M is going to be the n by n matrix. Remember, n is the dimension of our vector space, but M is going to be the n by n matrix whose columns M, by the way, is the transition matrix from B prime to B, because the input, when you multiply by B prime, you get out something in B double prime, something with respect to B double prime. So M, sometimes it's convenient to write M as the transition matrix from B prime to B double prime. Sometimes you see the subscript like that. Anyways, M is going to be the matrix whose columns are, what you're going to do is you're going to take the basis vectors for B prime, so V1, V2, all the way up to Vn, and figure out how do you write those with respect to B double prime. So the first column in M is going to be the vector V1 with respect to B prime. The second column in N will be the vector V2 with respect to B double prime. All the way out, the nth column in M is going to be the vector V sub n with respect to B double prime. And so sometimes we write this matrix M as the matrix whose columns are V1 with respect to B double prime, V2 with respect to B double prime, all the way out to Vn with respect to B double prime.